Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I think we should start. So it's my pleasure to welcome Sean Kakady this morning from MSR New England lab. So Sean probably doesn't really need introduction, and people here probably know him already. Sean has done a lot of work in computational learning theory and also other works. And today, he's gonna teach us how to use tensor decomposition for learning hidden variables models. Sean.
Okay. Yeah, it's fun to be here. I'll be around for the week, so if any of you want to chat, we can continue discussions. So how do we learn models with hidden structure? This is really one of the questions we're facing in a lot of practical applications, even from simple setting to really complicated settings in, say, machine translation. So let's just start with two basic examples for mixture models, which is mixture of Gaussians, which I think we're familiar with. So here we're going to see data like a bunch of point clouds, and we'd like to figure out the means of these point clouds. Okay. And another standard example are these topic models. So there we can think of having a collection of documents, and each document is about one or more topics, and we think of the document as being like a collection or a bag of words. Okay. And you can think of these two as like canonical mixture models. And how do we learn them? Learning is obviously easy if someone gave us the labels. Someone told us which documents are about which topics, it's easy. But if we don't have these labels, how do we learn? Okay, so let's start by just looking at what's used and what's known. Right? So oftentimes it's used in practice as EM. It's a very natural algorithm, or k-means. And what do? We guess the cluster assignments or the parameters, assign the points to various clusters, and iterate. And then there's various sampling-based approaches and MCMC approaches. And a lot of the practical algorithms essentially do inference and learning. So as they're learning, they try to figure out which points are assigned to which cluster. And at some level, this seems intuitive, but this might also be part of the difficulty in learning, because we're trying to figure out this inference problem. And inference is hard in some of these models. Like in the LDA model, like if you have multiple topics per document, just solving the inference problem is hard. Okay? But that's practice. What about theory? What's the upper and lower limits we know about learning? And there's actually been some really nice work recently by Adam Kalai, Ankur Malhotra, and Greg Valiant. So the first thing these guys showed is, let's just make the problem simple. What do we know about a mixture of two Gaussians? This is about as simple as it gets. It turns out even that wasn't known. And what they showed is how to learn a mixture of two Gaussians in poly time when the Gaussians could overlap. Because once things overlap, that's when things start becoming difficult. Actually, even when they don't overlap but are close, it becomes difficult in high dimensions. But in just 2 dimensions, they gave a polytime algorithm, which was efficient. So at least that case we know we can solve. But k was 2, so you can easily be exponential in k, where k is the number of Gaussians. Okay, so there's kind of a search-based procedure on a line. Okay. So subsequent to that work, there's some really nice follow-up work by Ankur and Greg, which actually, in a sense, was a negative result, where they showed it seems like you actually need exponential in the number of Gaussian samples to learn a mixture of k Gaussians. And this is an information theoretic lower bound. And this seems bad. And the point is, if you have k Gaussians which overlap, but not like right on top of each other, but by a reasonable amount, they actually showed you could potentially need many, many samples to learn this thing from an information theoretic point of view, which basically says computationally you're hosed too. So this looks bad right now, and is a really nice construction by Ankur and Greg. And to some degree, this talk is going to contradict that, because I'm going to argue that for kind of a natural case of mixture of Gaussians and these topic models, we can come up with a closed form and efficient estimation procedure. And this is kind of interesting for a number of reasons, which people are getting a little surprised by, because this is a non-convex problem, and the solution we're coming up with is non-convex, yet it's closed form. It's a pretty simple approach because it's based on linear algebra techniques. We aren't solving inference in the learning process, and this is handy when we start looking at these topic models with multiple topics in them, because sometimes inference is hard, but somehow we can do things greedily and still figure out what the topics are with this kind of closed form estimation procedure. We'll come up to this question of how do we avoid this lower bound, because I'm saying we could do things in closed form and nicely, but I just gave you this lower bound. And it extends to a number of other settings like this LDA model, which is a very natural notion when you can have multiple topics per document. Okay, and we can get a closed form estimation procedure for that, closed form estimation procedure for hidden Markov models, and I'll discuss some generalizations of these ideas to structure learning, like in these models used in linguistics and Bayesian networks. But most of the talk is really going to focus on these two simple models and understanding how we learn them. And basically, the proof is very simple. It's geometric, and I think we can really understand how to learn these things. So let's just go slowly and definitely ask.
Global optimum. Still local optimum, but efficient.
No. Global optimum. Efficient in closed form. So we'll see what that means precisely, but there's no local optimization here. This is global optima for estimating the parameters. Okay? But again, we'll see what we mean here because we have sample data, and there's questions about the efficient statistical rate and so on. But nonetheless, I'm going to stand by the claim that it's a closed form.
Initialization?
No initialization. We're not using EM. So we'll see, and that's the point. We aren't doing inference. It's more like a greedy approach. But let's see how we do that. Okay, so let's just start with some definitions, but definitely ask questions to the talk because I think these two examples are simple enough that we should be able to understand the proofs and everything. Okay, and I want to do these in parallel because they share a lot of similarities. And this is the one slide of notation. I think this should all be reasonably clear, but definitely ask questions. So for the topic model, we're just going to consider the single topic case. But let's go through the case of mixture of Gaussians and the single topic model. In the mixture of Gaussians, we think of having k centers, mu1 to mu k. These are points in a vector space. And in the topic model, let's think about having k topics. Okay? And I'm going to use the same notation. So the topic case, each of these mu i's are a distribution over words. Okay? So you're good with that? Okay? And then now we're going to think about how we generate a point. So in the mixture of Gaussian case, we first sample some cluster with probability wi, so that's my parameters. In the topic case, we're going to decide on a topic with probability wi. Okay? So that's why they're kind of analogous. In the mixture of Gaussian case, what do we observe? We observe the mean corrupted with spherical noise, because that's the case I'm going to consider. I'm going to consider the case with spherical noise. And this really is the underlying probabilistic model of k-means, right? And so k-means, what do? You assign things to the closest point. So this we can think of as the probabilistic model for k-means. Okay? So we just see a point corrupted with noise, and we're going to see many such points. Okay? So in the case of topic models, we're going to see a document, and document's going to consist of m words which are sampled independently from this topic. Okay, so it's an exchangeable model. So our document just consists of m words, and they're all sampled IID from ui. Okay, so at this level, we kind of see some distinctions between these two models. In the mixture of Gaussian case, we're adding noise to one of the means. In the topic model case, we get many words drawn independently from the same probability distribution, the same hidden topic.
Multinomial model?
It's a multinomial model, yeah. That's right. It's a multinomial model here, and they're independently. So they're exchangeable, and this is kind of why it's a bag of words model. It doesn't matter the order in which you see the words. We see this collection of samples.
But this is not the common. You put single and parentheses in there to indicate that this is not the topic models that are commonly used in practice, where you have a mixture of topics associated with each.
So we're going to come back to the case of multiple, the LDA model. I mean, this is one of the standard models used, but we often like richer ones, like LDA. But we'll be able to handle that as well. But in terms of understanding what's going on, I think it's actually helpful to consider these two in parallel because these are really one hidden mixture component. And the learning question is we're just going to see a bunch of samples. And what we'd like to recover are the means or the topics, the mixing weights, so these are just real numbers, and sigma for the case of the mixture of Gaussians. So the questions here, about this. And I like this because we kind of see how these models are similar and how they're different. And the main difference is the topic model, we get multiple samples from the same hidden state. And here we kind of get this a different notion of noise. So we good? OK. And Nikhil?
Yeah, topic model, you only see all the samples are from just one.
No. So we see multiple documents. So this is sorry. So this is one. So in the mixture of Gaussians, one x is a point. Okay. In the topic model, you see multiple documents. So think of the analog of x here to be m points here, and we see multiple documents.
So each point here is corresponds to one document.
Yes, each point here corresponds to one document. You can think of a document as this collection of words, and that's analogous to one of the x's.
And the dimension components correspond to individual words.
So let's go back to the dimension components. Right now I just think of these as discrete, but we'll formalize that later, how to think about it correctly. But we're good with the model? OK, good. So how do we learn these things? Okay, and learning is we have these sampled points. How do we figure things out? Okay, and there's a lot of work that's been done on this. I'm not going to go through the details of all of this work, but there's really a ton of work from the theory and ML community trying to figure out how to learn mixture of Gaussians, back from a really nice paper by Chandroy over a decade ago. And a lot of the work was really on a case where the Gaussians are very well separated. They don't overlap at all. And then what kind of approaches can we use to figure this case out? But they heavily relied on a ridiculous amount of separation. And then there's some work where they can actually overlap or where they're much closer together. And most of these are basically more like information theoretic results. And they're all typically exponential in k, where you're searching all over the place.
So how do all these methods differ from its original Dempster?
Well, these are all, OK, right. So all the ones I've listed up here are mostly theory results where you're trying to find the global optima. Or maybe not the global, something provable. Rather, you care about computation, which is why they're all either exponential in the number of topics, or the clusters are very well separated, and even there it's tricky for what to do.
Yeah, but basic procedures remain the same.
No, the procedure for the ones with a lot of separation are a bit, they're more based on distance-based clustering, where you kind of, some of them introduce the right notion of using linear algebra approaches, but all of these are quite different because no one has a very good understanding of the EM type approaches and how to, but these are a lot of its theory. And some of them give interesting algorithms or the right insights. For topic models, there's also been a lot of work. So Christos and Santosh, some other people had one of the early papers on how to view topic models as a matrix factorization approach. There's been some really nice work by Joseph Chang, which kind of heavily influenced our work, more from phylogeny trees. And even recently, there's been some nice work by Sanjeev Arora on the multiple topic case, looking at this as an NMF problem and how do we kind of do non-negative matrix factorization. But again, they can prove it with only separation conditions. So there's a lot of work. You can ask me later on about details of it. And to some degree, we're going to take a pretty different approach from a lot of that work. So let's just back up and forget about sampling issues and just start thinking about identifiability. And let's go back to this old idea before maximum likelihood by Pearson. So Pearson was the old statistician. He's like, how do we estimate models? And his idea was something called the method of moments, which is we see averages in data. How do we figure out the parameters which give rise to these averages? And going back to this multiple topic case, we started addressing this by identifiability questions. So what's the question here? Let's look at our moments. For the mixture of Gaussian case, the first moment is the mean. The second moment is the expected value of XX transpose. The third moment is this tensor, and they just keep getting bigger. For topics, we can think of the moments in a very natural sense. We can think of the first moment as corresponding to have documents with one word in them. We think of the second moment as documents with two. Suppose we had an infinite collection of documents with two words in them. What do we know? Well, we can figure out the joint distribution of two words in a document. We think of the third moment as the joint distribution of 3 words in the document. And now forget about sampling issues. We can just ask an identifiability question, which is how many words, how long do documents need to be before the parameters are well specified? Because if every document contained 1 word in them, and I had an infinite collection of documents, I would know this exactly. But it's not identifiable, obviously. Right? You can't figure out the topics if every document has 1 word in them. Okay, so we can ask this even more fundamental question, which is, suppose we had exact moments, when are the models well specified, and what order of the moment suffices to nail it down? And this is an interesting question when you have multiple topics per document, because now the question is, how long do documents need to be? Right? Say if every document had 5 topics in it, out of, say, 100 possible topics, how long do documents need to be before the model is identifiable? This is an information theory. And this is independent of sampling issues. And for the most part, let's just proceed for now, given that we have exact moments. And we want to address the identifiability question, and then we want to see, can we invert these moments efficiently? Can we take these moments and figure out the parameters? And you should note that these we can think of as all as either matrices or tensors. Okay, because this is this is like the bigram matrix, and this would be like a trigram tensor. Okay, so we good with that? So this is an even more basic question. Right? And this is what I mean by closed form solutions. I'm going to show you can easily answer this question. Okay, good?
So this moment of using generating function to do it, is that?
We'll see. No. Okay, so now let's just look at why I'm comparing these two, and just to use some vector notation because it keeps us on the same footing. So the mixture of Gaussians, we've got k clusters. We're in d dimensions in the mixture of Gaussian case, or we could have d words. Typically, we think of d being bigger than k. Okay, we have more words than topics, more dimensions than clusters. Okay, the mixture of Gaussians case, what's the expected value of x given we're from cluster of I? It's just the mean. That's the definition, right? For the vector notation, it's helpful to think of words, like this is the first word, as these hot encodings where this says the second word is on. Okay. Why is this handy? Because if we use this encoding, we can think of these mu's as probability vectors. So these are d-length vectors which sum to 1. And then we can think of the probability of any given word, given that we're from topic I, is just being mu I. Okay, so this is just the expected value of a word given topic, and this is just mu I. This is why vector notation is handy, because it kind of keeps things on the same footing. Okay, the noise model here is obviously different. The noise model here is spherical. The noise model here is multinomial, and it depends on the particular word we're getting. Okay, but that's just notation. Are we good with that? Okay. Okay, so now let's just start looking at these moments and trying to figure things out. Okay, what does the first moment look like? Okay, well, in the mixture of Gaussian model, it's just the average of the mu i's, it's the data center, and the topic model is just the average of the topic probability vectors. And obviously, the model is not identifiable from this because, this is always specious arguments, but parameter counting suggests it's not enough. And there are definitely problems with parameter counting arguments, but nonetheless, we know, the mean isn't enough. Okay, we good with that? Forward ho. All right, so let's look at the second moment. Okay, so let's look at the mixture of Gaussians model. We're looking at, I'm going to use this kind of a outer product notation instead of XX transpose. So what is the second moment of mixture of Gaussian model? It's the expected value of XX transpose. Each x is a mean plus noise, right? So what you get for the mixture of Gaussians model is basically a contribution of how the means vary, right? Because you've got this picture where you've got these means which lie in subspace. Actually, I'm going to put the x as the means. And then we've got kind of points lying around the means. Right? Okay. And the contribution for the second moment is kind of how the means are configured with respect to each other, plus the sigma squared times identity matrix due to the way due to the variance in the points. Okay. Now, something really nice happens for topic models, sort of discussions with Paul too, when you have kind of cross correlations and matrix. So if you look at the joint distribution between two different words, these words are sampled independently conditioned on the topic. So the noise is independent. So the joint distribution of two words, if you view it as a matrix, is just the weighted sum of the means. Because it's just, if you condition on the topic, the noise is independent. So it's just the expected value. This is just the expected value of x1, x2. With condition on the topic, they're independent. And the expected value of x given the topic is just mu I. So the joint distribution of the bigram matrix is just the average of the mean transpose. Yep.
I might be missing something. So you said in the beginning that in the topic model, you have m words in each document. Is it that the dictionary is of size m? Or
No. The dictionary is size D, and you get m samples from the document. So literally the document is just,
But then each word appears once or multiple times, because if each word you
No, this is, just take the first two words. So in this one, suppose the document just has two words in it. I'm looking at the joint distribution.
It's not x1 and x2 are not different words in the vocabulary.
No.
Whereas
X1 is the first word, x2 is the second word. Okay? So we're looking at the joint distribution of the first word and the second word, and those two are independently drawn given the topic. So the average value of x1, x2 transpose is just mean and mean. Think of a mixture of Gaussians case. If we could get two different samples from the same Gaussian, then these noises would be independent, and that would go away. Okay?
Another question. You use the term being identifiable, and you said that from the means in the previous slides you can't identify.
Okay, right.
What exactly do you mean?
So what I mean by identifiable is there are two different models which could give rise to the same means. So if you only knew the means, could you figure out the parameters?
But in your model, in your kind of k-means model,
Yeah.
Two clusters differ only by their means. So if I know the mean, I can identify.
No. So if in the mixture of Gaussians model, if you just knew the global average of the means, all you see is, in this case, the global average would lie somewhere here. If you just see this point, you can't figure out those x's. The means, yeah, that's exactly. So you just know E of x. And now we're going to look at E of xx transpose, and what we get is this. And what we get in the Gaussian case, so the topic model case is this. And now we see the first distinction because this thing is a lower rank matrix. What's the rank of the bigram matrix? It's k, it's the number of topics. Whereas this thing is full rank, it's dimension d. Okay? This is the first distinction. And this is handy. Exchangeability is really a wonderful property. Being able to get many samples that are independent conditioned on the same state because we get this low rank matrix. It's still not identifiable because basically all we learn is intuitively is basically, you can think of this geometrically as what we learned is an ellipse for where the means lie. It's kind of what a second moment matrix tells us. We basically say, we basically just figure out an ellipse, which is like the covariance matrix. And we don't really know anything past that. It's just kind of a rotational problem. But we're getting close to the right number of parameters, but you can actually show it's not identifiable. And it's not identifiable in the worst sense. It's not like, it's basically every single model is not identifiable. It's not just a few points get confused. Yep.
Sorry to jump ahead, but should I expect like when k squared is less than d that will be okay in the multi-topic case?
No, actually, we'll be getting there in a second.
Okay.
Parameter counting suggests, okay, well, how big is this? This is size d squared. And how big is 3d cubed? Well, d cubed has a lot of parameters in it. So, but this is definitely fishy because there's some models where are just fundamentally not identifiable even when parameter counting arguments work out.
I should be clear, like when k squared is less than d, the
I see.
bigram matrix will still be low rank.
So think, well, this is always low rank. Sorry, this is only low rank when d is bigger than k.
Right, yeah.
So it's not k squared versus z, it's d versus k.
Right, in the single topic case, but in the multi-topic case,
No, this one's going to be surprising. So this,
Okay.
so this one
hold
will
it.
break your intuition. This is why the identifiability question was really nice to us, because when you have multiple topics, like how long do documents need to be before you can identify it? And forget about computation, because we didn't expect an efficient algorithm. I just wanted to know the exact answer to this question. And it had to have an exact answer, but we couldn't for the life. Because some of the difficulty with identifiability, sometimes it's very hard to make identifiability arguments that are non-constructive. So there's really beautiful theorems from the 70s by Kruskal on how to do this, but they're very difficult because they're existence proof. So they're kind of, they're interesting questions, but we'll definitely get to that.
That's just one more higher level question. I mean, now you're talking about moment method, but generally, moment method is not as good as maximum likelihood method.
So let's get back to that. So there's kind of a long debate between statisticians between these two. And Fisher basically argued the moment methods. So Fisher basically argued maximum likelihood was more efficient.
Consistent.
Yeah, it basically is Cramer-Rauer, so it uses the samples better. But the point is, we kind of knew moment methods were easier to use, like even in simple examples. Like if you look at Duda and Hout, the first edition, I think it says, for some of these problems, you want to start with a moment method and then use Newton. And then kind of the modern versions of statistics, by modern, more like theory statisticians, they said, do method of moments, because maximum likelihood isn't consistent, and then do a step of Newton. And then they argued that was as efficient as maximum likelihood, because maximum likelihood does stupid things with infinities. So the best thing to do for getting the constants is they're basically consistent with each other. So do the method of moments, then do a step of Newton, because it's a little local optimization, and that's as good as maximum likelihood to first order.
Global optimum that you mentioned earlier on.
So that's what we're trying to do.
In terms of moment, not in terms of maximum likelihood.
We'll get to that in a second, but we're trying to solve forget about samples right now. Let's figure out how to solve the moments. And for now, let's drop the mixture of Gaussians case. Okay, we'll come back to it because it's not low rank. Let's just proceed with the topic model case, and then we'll come back to the mixture of Gaussians. Okay? Okay, so again, now we should we see what's going on. So if we have this trigram matrix, what's it going to look like? Well, the noise is independent. We're just going to get mu, mu, mu. Right? So what we get so now suppose documents have 3 words. What do we get? Well, we know, I'm just going to define M2 to be the bigram matrix. M3 is going to be the trigram probabilities. And it just looks like the sum of wi's mu, mu, mu. So it's this d cubed size beast. Okay? And it's the same argument. The noise is independent. Okay, so now how do we figure out the mu's from this? Okay, now let's just work in a slightly better coordinate system. But basically, this is the problem right now. How do we solve this structure? We see a matrix that looks like this. We don't know the mu's. And we see this d cubed size object that looks like, we know it's guaranteed to look like this. But we don't know what these mu's are. How do we figure it out? Now, geometrically, let's just think in a nice coordinate system. Whenever I see a matrix, I like to think about isotropic coordinates. So let's just think about transforming the data so that this bigram matrix is the identity, and it's low rank, so that means when we transform it, we're going to be working in k dimensions now. So just take the bigram matrix, make it look like a sphere. That means we're going to project things to k dimensions, and we have k by k matrices. And when we do that, we're going to do the same linear transformation of the tensor, which means the equivalent way to look at this problem is we know the second moment is isotropic. It's a sphere. We have a third moment that looks like this, where now we're in k dimensions. And what this transformation to a sphere does is it makes these means orthogonal. Okay, so basically, in this problem, we're now working in a coordinate system where these x's are orthogonal. And this is it. Someone says, look, here's a k cubed object, which is pretty small. It's guaranteed to have this decomposition. You know they're orthogonal. What are the means?
No,
Okay.
Decomposition typically means that you decompose a tensor three-dimensional array.
That's what this is. This is a
But that's three-dimensional. It's decomposed into two-dimensional array, and you sum them up.
no. This is a this is a three-dimensional decomposition because this is each of these are d cubed. So we know such a decomposition exists for this tensor. It's three-dimensional. How do we find it? Okay, so let's.
I'm going to project down to two-dimensional and stand down to.
No, I'm not gonna. I'm not gonna do that. But there's many different ways to do it. But that's the question. So we've really just reduced this question of how do we do this decomposition. Okay. So just back up a second and look at things as linear algebra operators. So let's go back to matrices. Remember this notation where we have a matrix M2. We can hit it by a vector on the left and right, which is, we can look at A transpose M2B. And for notation, I'm going to write that as hitting M2 with A and B this way. And just usual matrix multiplication means we just sum out the matrix over those coordinates. And for tensors, we can also think of these things as trilinear operators. We can take a tensor and you can hit it with three vectors. And just in the same way you do matrix multiplication, you just take this tensor, which has three coordinates, and sum them out over these three vectors. Okay? So this is exactly, so it's kind of linear in each of these operators, right? It's multilinear. Okay? What's an eigenvector of the matrix looking at in this form? Well, if it's you hit it with a vector, you get back the same vector scaled. Now there's a generalization of eigenvectors for tensors, where it's just hit the cube now rather than a square, hit it twice with a vector, you're going to get back a vector because, right, you're summing over three things. So if you hit it twice with a vector, you'll get back a vector. And we're going to call it an eigenvector if that direction is proportional to the direction we hit it with. Okay? So this is actually pretty well studied in various areas of mathematics and other areas. The problem is tensors are horrible in a lot of ways in the most general case because they don't inherit a lot of the nice structures of matrices, but we can still define them. And there's a kind of active area of study as to what these things look like. But that's a definition. Turns out for our case, they're well behaved. Okay, so what's our case? Our case is we have this problem. We know this cube looks like a sum of orthogonal vectors. Okay, any guesses? Well, what are the eigenvectors of this Whiten tensor? Okay, so let's just hit this M3 with two vectors v. What does it end up looking like? Well, it ends up looking like, this beast was w mu mu mu. We hit it v on the mu's twice. It looks like w v dot mu twice squared times mu I. And if we want to find an eigenvector, this had better be equal to lambda v. Okay? So let's suppose mu was mu1. They're all orthogonal. So I put mu1 twice in that expression. What do I get on the right-hand side? Well, the mu's are orthogonal. So what do you get? Yeah, you just get w1 times mu1, or w twiddle 1 from the transformation. So the only, and this is it, that basically all of the tensor eigenvectors, all the topics. Exactly, they're projected and they're scaled, so it's easy to unproject because we know the whitening matrix. We just slap it back in d dimensions, and then we can figure out the scale because we just make it sum to 1, the probability vectors. Okay, and what was the assumption we needed to get this to work out? Well, what did I do? Well, I made things white. When does that work? I need the topics to be linearly independent. That's the only assumption. Because obviously, if one topic is in the convex hull of the others, this might be problematic because then it's, there's even identifiability questions. But as long as things are well conditioned, which basically always occurs in general position, this is a minor assumption. So as long as the topics are linearly independent, which is minor, all of the tensor eigenvectors are the topics. This is the short answer. It's a very clean statement. And the reason tensors are nice to work with is because for this particular case, we have this nice tensor structure. In general, tensors are a mess. But this is about the nicest possible case.
So you stop at the third moment. Do you go fourth moment?
No, the third moment suffices to identify it. And this is the decomposition you need. And there's kind of no multiplicity issues either. It turns out, as eigenvectors, if you had the same eigenvalue, linear combinations are also eigen. There's no issues here because even if all of these w's were the same, it doesn't cause problems because of the way tensors work. Because of this cube, you can't get linear combinations being eigenvectors. Yep.
Sorry, is this limited still to the 2 Gaussian case, or is this?
We dropped the Gaussian case for now. This is for the topic model case with 1 topic per document.
But the cardinality of the topic can be arbitrary.
The cardinality can be arbitrary, yeah. So now the statement is you just need documents of length 3, any number of topics as long as they're linearly independent, and this is kind of the closed form solution, which we can think of as an eigenvector problem. Yep.
So do the lambdas suggest how many topics to pick?
No, the topics are going to come from the rank of the bigram matrix. Basically, you just look at the rank of that matrix, and that's the number of topics.
So any analogous of this for MOG problem?
We're going to get back to that in a second. So now the question is, what happens in mixture of Gaussians? What happens in LDA, and kind of richer models? But this is a clean way of understanding. What about an algorithm first now too? Because can we solve this thing? You know, we know how to do this for matrices. General ones are hard, but it's basically known. You know, we did analysis now, just basically analogs of the power iteration. You just hit it twice, repeat, because you want to find a fixed point. This is exactly how matrices work, and then deflate. And this thing converges insanely fast because it's even faster than the power iteration for matrices, which is like log 1 over epsilon. This is like log 1 over epsilon. Basically, this powering means you converge extremely quickly. Okay, so it's a very fast algorithm. Different ways to view this, which I find kind of interesting from a geometric perspective, is we're basically maximizing skewness. You can view that eigenvector condition as saying, it's almost like a subgradient condition, which says maximize M3 hitting it with V 3 times. Okay, which is like kind of maximizing the variance in the third moment. Okay, and it's kind of like finding the spiky directions. And that's kind of another way to view it. And this is why it's greedy, because it says all local optimizers of this third moment are the solutions we want, which is why you can kind of rip them off one at a time, because kind of every spiky direction is the one you want. And so, you know, there's a lot of different algorithms which are efficient because they're greedy. These are very similar decompositions from those studied in ICA because somehow the same tensor structure arises in that setting. So we understand it. And we also understand some of the statistical questions because if we don't have exact moments, you just use plug-in estimates, but it's just a perturbation argument. And the stability, it kind of just depends on the, you know, how overlapping the clusters are, but that's real. Okay? But now so we're good with that. This is a minor. I mean, the real thing is understanding the closed form structure, and the rest is perturbation. But now let's go to if we're done with that, we should look at the mixture of Gaussian case and the multiple topic case. Okay, so we're good with this? And this is pretty clean. I think we hopefully understood the proof and everything. So now what about the mixture of Gaussians case? Okay, so let's go back. So there's this pesky sigma squared I. And if we look at the third moments, we're going to again get problems. Okay, but what's sigma squared? Can we just figure it out? It turns out, yeah, suppose D was bigger than K, strictly bigger than K. So the previous algorithms worked if D equaled K with the topic ones. But for now, I just suppose D is like K plus 1 or bigger, which is always the case, right? Like a picture like this. Well, sigma squared is just the variance off of this subspace. Okay, so, right, because basically in the subspace, if I look at the directional variance, I get a contribution for how the means vary and the way the points work out. But if I look at the variance kind of in a direction orthogonal to the subspace, the only contribution from the variance in that direction is sigma squared. Okay, so that actually, what that means mathematically is the minimal eigenvalue of this matrix is sigma squared. Because these things lie in a k-dimensional space. Just to look at any direction orthogonal to that, which will happen if you look at the minimal eigenvalue, or just the k plus 1th eigenvalue, that's sigma squared. So we know it's sigma squared. It's just the minimal eigenvalue of that matrix, which we know. Okay? And we need a dimension to be 1 bigger for that argument. Okay? So it's estimable. So we can just subtract it out. So we can basically figure this beast out. And the way we do that is we look at the second movement matrix, we figure out the noise, get rid of the noise. Yep.
So why is it guaranteed to be the smallest? What if WI is really tiny?
See, the point is you're going to use an orthogonal direction because this is a PSD matrix. So hit this thing with any direction V, right? You're going to get V on this guy. But if we can guarantee the V's to be orthogonal to this, we can get it to be 0. So the minimum, see.
Okay,
right.
I see.
So that, and all I'm saying is geometrically is you can pick out the variance off the subspace without, just by minimizing the variance. So, yeah.
I see. So there will be some dimension. Okay.
Yeah, if it's greater. And it turns out there's a cheap trick that even if D equaled K, which was the case we wanted to be linear, you can still do it because it's a very natural point that actually, let me just go back here. I don't want to show you the mess. Basically, if you just look at the covariance matrix, so when you subtract out the mean, sigma squared is the minimum eigenvalue of the covariance matrix. So even if D equaled K, you can still figure out sigma squared. It's just the minimal. So forget about that case if that's not clear. But sigma squared is known. Okay. So we can get rid of that. Now what about for the third moment? Because if we look at the third moment, it's not just mu, mu, mu. You're going to get extra junk. Okay, but let's just look at what that is. So let's just go to one dimension. Suppose we're in one dimension and we have a random variable which is a mean plus Gaussian noise, where n is 0 sigma squared. What's the expected value of x cubed? Well, we get one term which is like mu cubed, right? And what's the other term?
Eta squared.
Expected value of eta squared is sigma squared times mu, and then there's a counting. 3. The expected value is this. So basically, the topic model, we want mu, mu, mu. I'm just doing it in one dimension. We get some extra junk. We get 3 sigma squared mu. But we know mu, because that's the first moment. That's E of x. And we know sigma squared. Granted, this is 1D. So now we just got to write this in kind of a tensor way. So basically, the way you think about, think of 3 sigma squared mu as equal to sigma squared times 1 times 1 times mu plus 1 times mu plus mu times 1 times 1. It's kind of a stupid way of writing it, but the only reason I say that is because, so M2, what do? We subtract out sigma squared times identity because we can estimate it, and then we just do the tensor version of 3 sigma squared to get rid of it, right? Which is basically, and these EIs are the basis vectors, so this is really just, mean 1, 1, 1 mean 1, 1, 1 mean, okay, minus sigma squared. And these two exactly have the structure we want. This means for the probabilistic model underlying k-means, we're done. We basically can construct this form. The eigenvectors are the projected means. Up to scale, so how do we unscale? It turns out you can get the scaling from the eigenvalues themselves in this case. But this is the main point. The main point is algebraically, the structure we have, if we just rip out the noise, is this. Which is pretty neat. And this is why we see the difference in this topic model is because we didn't have exchangeability, the noise correlates, so we've got to futz around with the noise because we can't get these low rank matrices, but it doesn't really matter. We just get this, and then we get a closed form solution with the exact moments. Now let's go back to Greg and Unker's result. They gave an exponential lower bound, but the way they did it is they put k Gaussians on a line in a configuration of a very particular configuration. And what that effectively does is, the assumption we needed to solve this problem is they had to be in general position. And k Gaussians on a line are not in general position. And so what's kind of nice, we actually know there's some gap in between that if they're not in general position, it could be bad. And if they are in general position, it turns out we only have a polynomial dependence on the separation condition. So by that I mean, in general position, they still could be close together, but we could look at the minimal singular value of the matrix of the means, and it's only a model dependence there. Where somehow, once they become unaligned, you could be exponentially bad in the separation. Whereas if they're general position, it's somehow polynomially bad. And you can kind of see why, because if they're unaligned, the third moment is still a number. So it's not identifiable from the third moment if it's a number. You have to go to a very high moment. And estimating very high moments is unstable. Now, that's only one algorithm, and they prove it information theoretically, so it's for any algorithms. But the intuition is nice. So that's how we got around the lower bound.
Elliptic Gaussians, you may not have this kind of nice property.
We don't know how to solve the elliptic case. And there, I don't even know how to prove hardness results. There are cases which I think statistically are fine to estimate, but computationally we have no idea. And I don't think there's any language for how to even understand hardness in these average case type scenarios. But anyway, for this very natural case, you basically have seen the proof. This is it. Okay? It's pretty simple. And the very last thing I want to do is look at this case of multiple topics.
Well, okay, but can you talk a little bit about like what the finite sample effects are?
Oh yeah, so that's basically basically the analog of a matrix perturbation argument. That if I'm only going to say poly, it'll appear in the paper for now. But basically, for SVDs, there's like Wedden's theorem and these kind of theorems of how accurate is an SVD if our matrices are perturbed. And this is just the analog. How accurate are these eigenvectors if the tensors are perturbed? And that's what I was referring to here. What it depends on basically are how collinear the means are, but in a nice way. And that's kind of real, because as the topics start becoming collinear, you're going to expect to need more samples. And that's because the stability of an SVD, even for the matrix case, the stability of SVD depends on the minimal eigenvalue. But it behaves kind of nicely in the same way our matrix perturbation theory is nice. And the only time it starts becoming bad is if it becomes actually degenerate. We don't know how to solve it. But it basically, it's all like 1 over root n and nice dependencies. But I'm not going to explicitly give those theorems here, but they will appear in the paper. And they're kind of dependencies one would expect. And I think even statistically, they're real. They're kind of information theoretic. But the point is they're mild, not like these exponential worst case things. So I want to look at...
And do you actually like, for a finite sample, for instance, you would use like the actual minimum eigenvalue for sigma squared, or do you like correct it?
So what I would do is I would first project it into k dimensions and use the minimum in the case space. Okay. There's actually a trick I would use. I would actually try to use a slightly different model for the mixture of Gaussians. We can talk about that later. I would look at it more like a topic model case, which I'll get to. Because this is more like a spherical case, and I don't know how to handle the There's another case of mixture of Gaussians I can solve. But maybe let's come back to that in the discussion section. Let's go to the multiple topic case, unless there...
You have yet to find the estimation formula for this.
No, it's the eigenvectors, so I can...
just do eigenvectors.
Yeah, just do the eigenvectors of the tensor. There are many different ways to solve that problem. In a sense, this is the moment I've set it up for you, and just go to town. The point is we know there are algorithms that solve this. They come from ICA. You can actually do this with 2 SVDs as well. So the earlier work, we were using kind of bad algorithms to do it, because you can kind of project this down to matrices and kind of, there's this term simultaneous diagonalization. That's another way to do it. But geometrically, once we understood this, it's like this is the structure. We know how to solve it. You can think of it as an generalized eigenvector problem, which is a really clean way to think about it.
The eigenvector become the mean of the estimate for this Gaussian?
The eigenvectors are telling us the means, yes. Up to scale, but we can find the scale, and then we can find the W's, and we found scale.
How about the estimate of sigma squared?
We got sigma squared because that's how we got these formulas. It's the minimum of the covariance mixture. So let's go to topics. So topic model case, if there's multiple topics per document, so now you can have a document like 30% cute animals, 70% YouTube or something like that. How do we figure this out? Well, what's the identifiability issue? If every document is about 5 words now, do we need 3 times 5, or how long do they need to be? And it would be bad if the moment had to increase, because in a sense, estimating higher moments becomes exponentially more difficult in the order of the moment. Okay? But parameter counting suggests third moment is enough. Still, even if you have a mixture of multiple moments, you've got d-cubed parameters in the third moment. And for a long time, we thought the LDA problem had to be exponential, and this is borne out because Sanjeev and some other theoreticians basically gave very strong assumptions to solve it. People did not think you could do this in closed form, but it turns out LDA, all you need is 3 words per document, and it's the same idea of just maximizing some third moment. So LDA basically, you have to specify a distribution over distributions, because now every document is about a few different topics. So it means, every document, you have to specify this distribution over distributions, and these LDA distributions are these kind of nice pictures where you have level sets here. So that's what this prior is here. So this pi is, rather than this document being about topic 1, this document is going to be about 30% cute animal, 70% YouTube. That's specified there. And that's this kind of distribution over the triangle, which has a particular form. In a sense, it's like the nicest possible form distribution you could put down for a triangle. And it captures sparsity because you could have pictures where these level sets kind of bow out. Okay? And the point is that, you just got to write down what these expectations look like. And one physicist you're working with, he was like, oh, it's not so bad. You just integrate some gamma functions. But the point is you just look at the structure of these things. And the same trick, like for the mixture of Gaussians, because now if you look at these correlations, you kind of get extra terms in a similar kind of way. And you just subtract them out, the stuff you don't want. And this kind of has nice limiting behavior where the kind of coefficients of the subtraction basically depend on like a sparsity level of the model, which is often set in practice. So the only parameter we need now is the kind of the sum of these alphas, which is often set in practice, and it's like an average level. It kind of determines the sparsity level. So if you know that, you can kind of determine what to subtract, and it kind of blends between 2 regimes. So when alpha goes to 0, you kind of go back to the single topic case where these go away. And there's more stuff here because it looks more messy. You get all the symmetrizations and stuff like that. But it's still easy to write. And as alpha becomes very large, what these moments actually end up looking is central moments. When alpha is large, what this thing ends up looking like, it looks like e of x1 minus the mean times x2 minus the mean. And same thing here. And that sort of should be the case because this triangle starts looking like a product distribution. So these 2 regimes are kind of nice. And I like this kind of maximizing perspective rather than the tensor eigenvector, because basically, you want to find these pointy directions. So this skewing is almost like a geometric problem of how do I find the corners of a convex polytope from its moments. There's always different perspectives are interesting, and that's basically what's going on here. I'm just looking at this Dirichlet distribution, skewing things a little based on the way the measure is put on the simplex. So the maximizers point to the corners. But that's it. So LDA has this closed form solution. You can kind of tweak these moments with lower order things which they have the same structure. The eigenvectors are the topics.
But it's a closed form solution for a different objective function, right?
If the moments are exact, it's just a closed form solution. That's what I mean. Okay, so if it's not a closed form solution, it's an inverse moment solution. But as I said before, at least in some cases in classical stats, we know if you did the moment estimator and then did a step of Newton, that is about as good as MLEs. And for these problems, it might actually be better just to there's often like infinity problems with MLEs. So in practice, it's actually kind of nice to use moment estimators and then local search on top of that.
So I'll finish with variational Bayes or something.
I guess inference is hard. So yeah, you'd have to do like sampling or variational after that. Okay, so that's LDA. And again, you raised a point. This is nice because inference is a headache in these models, and it's hard. And it was very important for this. The single topic models, a mixture of Gaussians, it's easy to do inference. These problems, it's hard because even just writing down the posterior is not closed form. Yet we can still solve it in this greedy way. So somehow we've gotten rid of inference in these moment approaches.
So what we do, you can do the same thing as you talked about earlier, right?
It's the same form of the moments, just figure it out any way you want.
Okay.
Use the eigenvector
So
method.
you get the eigenvector, but you have to convert the eigenvector into the parameters.
Well, the eigenvectors are the distribution, so you just unproject them and normalize it. Okay. So,
Is that when you have a prior also on the word distributions?
no prior on the word, there's a prior on the topics distribution. Because the word distributions, we think of them as parameters, those are the topics. So there's no prior there.
Yeah, so that gives you global optimum for the moment.
I mean, in a sense, don't think of it more this identifiability viewpoint rather than global optimum. If you know these moments, you've uniquely specified the parameters, and we have a closed form way to get it, and then it's a kind of a perturbation argument to figure things out. Okay,
Now,
so
to turn that into maximum likelihood, you need, as you said earlier, you need the second.
you need to do second order. That's going to be close to maximum likelihood. Because you're basically chasing the maximum likelihood cost function at that point. But a step of Newton is pretty darn good. So that it will get you this kind of
Local optimum for
not local. That'll be actually
for maximum likelihood.
it's not going to be low. It's going to be close to the maximum likelihood solution. It's going to be close to the global maximum likelihood solution.
Is it guaranteed?
No, it's not
How can you
guaranteed.
guarantee that?
Because the parameters are close. You'd have to do some like convexity argument.
How can it be the global optimum for maximum likelihood? How can you even guarantee that?
Yeah. So this is this wacky.
Did you
Okay, so now we're getting close to the discussion section, so I'm just going to answer this, and then. So this is where it's funny with these average case hardness results, because we know maximum likelihood is NP hard in general. Yet, what this is saying, I am going to argue that this will give us something close to the maximum likelihood solution, because we're getting the true parameters, and I can give you a poly sample size. So even without doing the step of Newton, I'm getting close to the true parameters. And the maximum likelihood solution, the global one, is also close to the true parameters. So what's the contradiction here? Well, the contradiction is this is like an average case result. It's saying if the points come from the distribution, then we can find it. And there are cases where we have average case results.
But you're completely ignoring the distribution disparity between what the data says and what your model assumptions are.
No, the hardness results are showing that there exists, if we could solve this problem for all point configurations, then P equals NP. This is not saying that. This is saying with high probability, for configurations that tend to look like the model is correct, those are the ones we can solve, which is why from a complexity point of view, it's very hard to start understanding average case hardness when the model is correct, because I think there's cases for these models where statistically, like in the mixture of Gaussians case, I'm sure there are cases where, when it's non-spherical, statistically it's fine, we know those cases, yet solving them we don't know how to do, and how you even prove a lower bound, we don't have. There's like only the permanent or something is kind of interesting cases we know how to give lower bounds for. But anyway, maybe get back to the discussion. So one more slide. I just want to say the idea generalizes to other models. So hidden Markov models, length 3 chains, you can estimate it with the same idea. You can kind of cook up tensors that look like that. Some other recent work on harder questions for like structural learning. So these models in linguistics called probabilistic context-free grammars. You see the sentence like the man saw the dog with the telescope. Is the man seeing a dog holding a telescope, or is he holding the telescope? And how you figure that out involves parsing problems. There's a wonderful set of questions here for how you learn these models. It turns out we made some recent progress in showing that even if you had infinite statistics, the general phrasing of these problems are not identifiable if you only see sentences, which is pretty frustrating. There's some work with Percy. Under some restricted assumptions, we can make progress on these models, but again, there's an interesting in-between for the restrictions we make and the non-identifiability of these models, which we'd really like to make progress on. Also some recent work on learning the structure of Bayesian networks with these models. So suppose you see some DAG, you observe these nodes here, you would like to figure out the structure, you don't even know the number of nodes or the edges. How do you even know this network is identifiable? We can look at moments and try to figure out what's going on. And here we actually need some new techniques even to just figure out identifiability. Because for example, suppose this network, these were the observed, went up this way. You get more and more nodes as you go up. you wouldn't hope this thing to be identifiable. So even just characterizing identifiability turned out to involve some graph expansion properties, and then combined with some moment ideas. Yep.
So just a question about these hidden Markov models. I was thinking this would be interesting for HMMs, but I was talking to Jason Eisman this past summer, and he pointed out that, so say I only look at adjacent trigram statistics.
Right.
How do I get identifiability on chains like A, B, B, B star A, or C, B, B, B star C? Say I have those two possible sequences coming out from my model, where the A is at the beginning and the end, but there's a sequence of B's that's too long in the middle.
So these are models where the assumptions could be wrong. Or you have to use, I mean, there's kind of these cryptographic hardness results that you can make long chains and kind of hide combination locks in them. And to some degree, the hope is these should be divorced in practice. Because if I see like some garbage fall and bang, something happens really far in the future, cryptographically, this is hard.
But these happen all the time in linguistic phenomena, right? Like I have agreement phenomena that can be arbitrarily long distance. Now maybe I should try to use tree-structured models.
That's right. So I would argue that hopefully for linguistics, the regimes we're in are not the cryptographic hardness regimes, but the delicacy is how do you kind of phrase the model to avoid that.
I'm not convinced that trigram statistics would suffice to capture some of these interdependencies either.
So in practice, they seem to work reasonably well for initialization. So Jeff Gordon's been doing a lot of work. Even in linguistics, Michael Collins has been actually playing around, not with these eigenvector methods, but with kind of earlier operator representations. He's been getting some reasonable results.
I mean, there are certainly things that you can capture, but I just, okay. Maybe
but I would argue these are modeling questions rather than fitting questions, which is why these models are very interesting. But now how do you fit them? So there's wonderful questions across the board here.
For the three length chains, what does it mean? Does it mean that you have only three observations? No.
The chains can be arbitrarily long, but you only need to look at the statistics of three things in a row to figure things out. Because it's the same kind of idea. You don't need to look at very long chains. It's just the correlations in three. You only have enough parameters, but you can actually uniquely, by third moment, you can kind of construct these tensors and figure out.
At the fourth moment, you don't have a solution for it.
No, if you have any higher moment, you can also solve it because it gives you the information about the third.
You talk about up to third moment. How about fourth moment? Do you have a solution?
Fourth basically have the same structure, so you can use higher moments as well.
It doesn't have to limit to three lengths. As you said.
Well, the thing is, if you have longer chains, you can estimate the three better. So it's even in LDA, if I have longer documents, I would just use the longer documents to get better estimates of my trigram statistics. I would rarely go beyond third or fourth. Third is good if you have kind of asymmetric things. If things are more like kurtotic, you want fourth. So maybe it's good to question soon. So in a lot of settings, understanding the tensor structure does provide us some interesting solutions for these problems. And kind of surprisingly, they're very simple solutions. And people in many different areas are now actually studying various algebraic properties of these tensors. So the paper for this stuff is going to be forthcoming. To some degree, it's all in previous papers. We just didn't really understand the tensor structure. We were solving it with this basically simultaneous diagonalization where we took the third moment, projected it to a second moment, and then we're futzing around with that way. They weren't really the best algorithms. But now we're realizing this is the structure we have, and there's actually algorithms from ICA. Like they've considered power methods. Like even Tong Zhang has some paper with Gulab, like 15 years ago with his advisor on tensor decompositions for how to do this. This is joint work with a number of colleagues over the years. Two particular people are Daniel Sir and Anima Anandkumar. Daniel has been working on me since the beginning of HMM stuff. He was an intern with me at TTI. He's a postdoc at Microsoft. Anima is faculty at Irvine, and she's visiting me now. Both those two are fantastic. They're terrific to work with and just talented colleagues across the board. So thanks a lot.
So related to the Bayesian network you talked about earlier with many layers.
Yeah.
So does that technique deals with this explaining away phenomena, somehow give some insight?
Well, right. So this is, in a sense, this is what we're trying to avoid when you learn these things, because somehow coupling inference with learning makes it difficult. When we think about learning Bayesian networks, I sort of don't want to think about these explaining away things in the same way. I don't want to think about which documents are about which multiple topics in the learning process. I want to, at least one way to, it's not the only way, other methods might be good, but it's a different way of thinking about it. What can we recover from just the average correlations? But for the learning the Bayesian networks, actually that paper just appeared on Archive maybe yesterday or today or something. But there, we actually need more techniques because somehow the problem with Bayesian networks is, this LDA model is almost like a one-level kind of model where these are which topics appear and these are the words which appear. And we have an explicit model of the correlations between these topics in the LDA model. The problem with these Bayesian networks is we have no idea what the correlation model is here at this level because we don't know what's above it. So what we're actually using there is some ideas of looking at a sparsity constraint, which is kind of what the expander condition is doing. And there's a paper from Colt this year, which is how do you take a matrix and decompose it into basically some kind of weight matrix and then some, but it's sparse, times some other matrix. There's a nice paper by Dan Spielman, and we're really utilizing those techniques along with some of these moment ideas. But even, the right way I used to think about it is like, what do these things mean to even be identifiable? And if you could make a formal argument for that, in many cases, I think that does reveal something about the structure of the problem, because if it's not even identifiable, that's sort of giving you some intuition as to what the hard cases are. And these kind of hidden variable models, identifiability is fundamental because we don't even know the structure of these things, and it's clear you can put in other nodes sometimes to give rise to the same structure. So it's just different techniques, though. Other questions? So I'll be around for the week, and it'd be great to chat with people because we are playing around with these as algorithms. People understand these algorithms in other settings, and they're very natural, particularly for features. It's just find some pointy directions in your data, right? It's like this LDA problem. The problem is if you try to do this in your data, if it's noisy, all the words lie really far away from the corners. But somehow, by averaging it is what allows you to say, I'm finding these pointy directions. So somehow, you can't just find the pointy directions like in the raw data because words don't lie anywhere near the, where they should be. And even documents of length 3, it'd be, if I say this document is about sports, history, literature, and dogs, and there's only 3 words in it, you'd be like, you're crazy, this is only 3 words. Yet so somehow you really do need to do these averaging techniques, and they're an interesting class of algorithms for initialization. So we have been toying around with it, and it's just another bag of tools we have. But if you're interested in playing around with it, it'd be fun to chat, and just more broadly, this set of techniques. Because, I don't think they solve everything, but thinking about any problem differently always helps us. And this is a new set of tools that I think should be complementary to other approaches.
All right, let's